You know, when we talk about AI, it's easy to get caught up in the flashy stuff, the super complex algorithms, the giant neural networks. But what if I told you the real engine, the thing that's actually driving this whole revolution, isn't the code, it's the fuel? Today, we're diving deep into the bedrock of AI, reliable data. Because it turns out the real secret sauce, the thing that gives you a genuine edge, isn't just a clever model. It's having clean, trustworthy, and reproducible information to power the whole thing.
That's a pretty dramatic statement, right? But it's something you'll hear from pretty much any veteran in data science. Data leakage is what happens when your model accidentally gets a peek at the answers during training. It looks like an absolute genius in the lab, but then it fails, just spectacularly, when it sees real-world data for the first time. It's a classic trap, and honestly, even the best teams can fall for it.
So, okay, data leakage, it's a known enemy. We have ways to fight it. But what about the problems that are way more subtle? The silent failures that are just lurking inside your data. Those missing values, the weird outliers, the tiny inconsistencies that don't crash your code, but are quietly poisoning your results from the inside out. Well, that's what we're going to tackle today. So, our journey has to start at the very beginning, in the messy, chaotic world of raw data. I mean, before we can even think about building a model, we've got to wrestle this information into shape. And the first and most common problem you're always going to run into is data that just isn't there.
Okay, check this out because this is absolutely crucial. Not all missing data is the same. On the left, you've got the simple kind, MCAR, which stands for missing completely at random. Think of a sensor that just randomly glitches out. The reason the data is missing has nothing to do with the data itself. In these cases, you can often just delete those rows and be fine. But on the right, that's the dangerous one, MNAR, missing not at random. The example here is perfect. Imagine you're studying a disease, and the absolute sickest patients, they stop filling out your surveys. The reason their data is missing is directly tied to the very thing you're trying to measure. So if you just delete them, your model is going to look at the remaining data and think, hey, this disease isn't so bad. You've just created a massive and completely hidden bias.
And that is exactly why, before you rush in to fill in, or as data scientists say, impute those missing values with something simple like an average, you have to stop and play detective. You have to ask why. Is it just a random glitch, or is there a deeper pattern here? The diagnosis has to come before the treatment. If you get that wrong, you risk making your data and your model so much worse.
All right, so we've talked about data that's not there. But what about the data that is there, but it just sticks out like a sore thumb? You know what I'm talking about. An age listed as 200 years, or a single purchase for $1 million in a data set where everything else is 10 bucks. How do you deal with these without just throwing away information that might actually be valuable? To really get why outliers are so dangerous, we have to talk about this concept called leverage. Just imagine you're trying to draw a single straight line through a cloud of dots on a page. A normal point, it doesn't move the line much, but an outlier sitting way off by itself, it acts like a powerful magnet. It has high leverage, and it can single-handedly yank that entire line towards it, completely warping the true relationship you're trying to find. So what's the fix? Well, there's a really elegant solution. Instead of just deleting the outlier, we can use a smarter mathematical tool, like the Huber loss function. Think of it like a really smart teacher. For small mistakes, it's super strict. It pushes the model to be very, very accurate. But when it sees a massive, crazy error, or outlier, it totally changes its approach. It switches to a much gentler penalty. It basically says, whoa, okay, that point is so far out there, I'm not going to let it completely mess up my grading curve. It acknowledges the outlier exists, but it refuses to let it hijack the entire model. Pretty clever, right? Okay, so we've dealt with the individual data points, the missing ones, and the weird ones. Now we need to zoom out and look at the whole process. Because it's not just about having clean data. It's about building a clean, reproducible lab for our experiments so that we don't end up accidentally fooling ourselves. Now, this slide right here, this shows probably the most common way data leakage happens. Let's walk through it. The big mistake, the wrong way, is to do all your data cleaning on the entire data set at once. Let's say you calculate the average value of a column to fill in some missing data. If you do that on the whole data set, you've just used information from your future test set to prepare your training set. You've peeked at the answer key. The right way is a very strict sequence. First, you split your data. Lock that test set away in a vault. Then, all of your cleaning tools, your scalars, your imputers, you fit them only on the training data. Then, and only then, do you use those tools to transform both your training and your test data. This is the only way to guarantee your test set stays truly unseen. And that's really the bottom line. The entire purpose of a test set is to be a perfect simulation of what will happen when your model encounters brand new, totally unseen data out in the real world. Any little step in your process that lets information from that test set bleed into your training process, it breaks that simulation and gives you a totally false and dangerous sense of confidence.
So how do we make that split reliable? Well, the common way is using a random seed, but honestly, it's super fragile. If someone just resorts your data file, or you move from one programming language to another, that same seed could give you a completely different split. It's really just an illusion of consistency. The much more robust pro-level method is hash-based splitting. You take a unique ID for every single row, like a customer ID, and you run it through a function that creates a consistent digital fingerprint. Then you use that fingerprint to decide if it goes into the training or test set. This guarantees that a specific customer will always end up in the same group, no matter how the data is sorted or where it's processed. That is true, rock-solid reproducibility.
All right, we're making progress. We've cleaned our data, we've structured our experiments the right way. But what happens next week or next month? How do we maintain this level of quality over time, especially when new data is pouring in constantly? This last section is all about moving from that one-time manual cleanup to a truly industrialized, automated system for maintaining trust. And this is really the core challenge of what people call MLOps, or machine learning operations. See, for our code, we have these amazing tools like Git that track every single change. But our data? It's often treated like this messy, constantly changing blob. So if your model's performance suddenly tanks, how do you know if it was a code change or if the data itself just quietly shifted underneath you? We need something like a Git for data. And the good news is, a whole ecosystem of tools now exists to solve exactly this problem. This slide just gives you a quick taste. Don't worry about the specific names, look at the different approaches. You've got tools like DVC that plug right into the Git workflow developers already love. For absolutely massive data, things like LikeFS give you Git-style branching for your entire data lake. The key takeaway isn't which specific tool to use, but the core idea. They all give you a way to snapshot your data, making your experiments truly auditable and reproducible forever. Now, being able to roll back your data to a previous version is a huge step forward. But what about catching problems the moment they happen? How do you defend against those silent failures? You know, like when another team changes a currency column from dollars to cents without telling you, or a data feed suddenly starts sending empty values. Your code doesn't crash, your program keeps running, but your model's predictions are now complete garbage. This requires a whole other layer of defense.
And this is where data quality testing comes in. The best way to think about it is unit tests for your data. This slide shows some examples using a really simple language called SOTA-CL, and look how readable they are. A freshness check can just say, hey, this data can't be more than 24 hours old. Boom! A stale data pipeline is stopped in its tracks. A schema check makes sure the columns haven't suddenly changed names. This takes quality control from being a manual chore you do at the end to being an automated, proactive gatekeeper that's always on watch. So, when you put all three of these pieces together, what do you get? You have the careful initial cleaning of raw data. You have the reproducible leak-proof structure for your experiments. And you have automated quality gates watching your pipelines. What you get is something incredibly powerful, an autonomous data reliability lifecycle. It's a system where quality isn't just something you check for at the end. It's an intrinsic, automated, and trustworthy part of the entire process, from start to finish. And that leaves us with one last big idea to chew on. As powerful AI models become easier and easier to get, and the computing power to run them gets cheaper, the models themselves might just become a commodity. So what's going to be the real, lasting competitive advantage? Maybe it won't be about having the most clever algorithm. Maybe it'll be about having the most reliable, trustworthy, and well-understood data engine to power any algorithm you choose.